Yeah, let's solve another medium problem today, and it's 1769, minimum number of operations to move all balls to each box. So we have n boxes, you're given a binary string of boxes, and n where boxes, okay, so if it's 0, box is empty, if it's 1, there is a ball in it. In operation, you can move one ball from box to the adjusted box is I know what is adjusted box is. Not that doing so, there may be more than one ball in some boxes. Okay. Return array answer. The answer is minimum number of operations needed to move ball. Answer is calculated initial state of the boxes. So we have boxes and output. First box, you will have to move one ball from. Okay, so we're moving one, and this is one. Oh, okay, so this is one, and this is one. 3. Yeah, because we have to 2 and 1. So we have 3. Okay, so I would say that first that I can think of it's brute force solution, and this, yeah, let's think of brute force first and see if we can optimize it somehow. So brute force will be quadratic time, and basically what we're gonna do, we're gonna our result I will be as sum, right, from 1 to n, and we in this sum we're gonna add one if boxes j, so j will be from 1 to n. Let's say j equal 1 to n. Yeah, it's better I cannot write some mathematical thing here, but yeah, j from 1 to n in sum 1 if box j equal 1, and we have to multiply it, right? So if 1 is 2 cells away from our box, it will be 2, right? If 3, it will be 3, and so 4. So this will be as absolute value from j minus I, right? And this is quadratic time formula for this. And how can we optimize it? And what we are doing, what work we are doing repeatedly. Like, for example, if we are doing some repetitive work, we are not, because we calculate every time as adjustment here, and its adjustment every time will be different, right? Because it uses I. Let's quickly implement this. Maybe it will be clearer for me if I write it in code, like where it will be where it could be optimizable, right? J, and we have to define a result as 0 multiplied by L, and yeah, and some kind of running sum, which is our whatever we're gonna have in sum. Yeah, we're gonna have some multiplier maybe. So I can say that multiplier equal 1, if boxes else multiplier equal 0. And what we're gonna see the maybe work repetitive work is when we have a 0. We don't have to calculate, right? But still we have to calculate for others. So even if we skip in 0, it doesn't matter. Then our running sum will be multiplied by absolute I minus j, right? And we assign result I equal running sum, and we return result. Still not working. So we are going through like boxes, and for example, we start from I will be this, right? And j will be this same, right? So we're gonna go, we have the same value, I minus j is 0. We are not including this one because we already have a ball in this cell, right? So we move in j and we have a 1, and difference is 1. So boxes of j equal 1. And then we multiply and, oh, okay, yeah, I understand my problem. Okay. Oh, it's working. Quadratic is working. Okay. How can we optimize it? Apparently. So this will be solution time. Solution A, brute force. So let's see how people did it faster. So their left count. Okay, so we are adding left count and left cost. Left count plus 1. Left cost is summarizing. Okay. And answer is left cost. Yeah, so this is ON obviously, but it's hard for me to say. Can I ask ChatGPT? Let's say I'm solving this guy. I'm trying to solve this one. How can I optimize my code and why? So instead of checking every box separately for each index, accumulate the operations while traversing from left to right and from right left operations. Number of operations needed to move. Oh, okay. So if we have this formula, right? But is there a way we can tell that result I equal result minus 1 plus right, whatever we have on the left with whatever we have on. No, not true. Okay. Left to right pass. So we calculate left operation and left count. Why? Okay, left ops. Number of operation needed to move all bolts from the left side. All bolts from the right side. But why are they calculating this? Instead of checking every box earlier, accumulate the operation while traversing from left to right and right to left. And then we're going backwards, and our right ops we adding right ops to okay, right operations. First loop accumulates the number of operations needed to move balls from left to right. Yeah, but so it sounds like we are calculating for every oh, okay. I think I understand. So we are going through from left to right. We are accumulating operations. So, for example, like this, similar, but this, so left to right. So we calculate left first. And left will be 1, 2. So our left operations will be 0, 1, no, 1, 2, 2. Excuse me. Then our right operation will be going backwards. 0, 1, and 2. So result will be 3, 3, 2, which is not correct. Okay, let's go back to code. Oh, so we are assigning before, okay, gotcha. We are assigning before the stuff happens. So this, and then are we changing it? Wait a second. No, we're not. So everything before happens, stuff happens. So Left in this case will be 0, will be 1, and will be 2. Right? 0, 1, 2. And backwards will be 0, 0, 1. So it will be 1, 1, 2, but not 1, 1, 3. Oh, come on. What's going on? And left count plus 1, and we calculating left oops. After every ball adds its distance contribution. Oh, okay. Now I understand. See, every ball adds its distance contribution. So if we have a, yeah. So if we have a, for example, three balls, right, on the left side, as we dragging them to the right side, every ball add 1 to its contribution. This is why we need to add the same at the end. Okay, seems seems really cool. Let's keep this one just in case, and try to implement what we learned. And we have to add left, right, left count and left as a these guys will be always here. So multiplied by L, and what we're gonna do first, we're gonna do this run. However, we're gonna add the left whatever we have. A left count, left sum. Let's call it left count, left sum. And left. So left count is 0, left sum is 0, and left is array, right? So we add whatever is left I, whatever we have into left sum. Then if boxes I equal 1, we increase left count, and at the end we add left sum, left count, right? Then we do the same for the right, and slightly different, but pretty much the same. So can I replace stuff? Oh, nice, left. Yeah, but I cannot change selection. Place all, replace it. Yeah, can change. Okay, let's quickly retype it. I love typing. What's going on? Okay. So we have right count, right sum, and we have right, and then right, we add right sum and right count, and the right sum we and the right count, and then yeah, and then we can say that here oh, we have to turn backward. words from L minus 1 minus 1 minus 1. And then the result will be, we also can say result I here, so we don't have to write another for each for loop. So will be whatever we have left plus whatever we have right. I kind of understand it, but yeah. And we return res. Yeah. Yeah, this is much better. So yeah, as we go, we accumulate some, and for left and for right, and we use it for result at the end. Yeah, that's it for today. Thank you for watching. Bye.